Similarity of matrices. So A is similar to B. We saw this. If B is M inverse A M for some matrix M. So we have lambda is equal to S inverse A S, because A is equal to S lambda S inverse. So we can just rewrite it this way. So we know that A and lambda are similar to each other, not merely in the shape of the symbol, but also by our definition of similarity. So similar matrices have the same eigenvalues, but not the same eigenvectors. So same eigenvalues. Let me prove this once more. B is M inverse A M. So A is that, and eigenvalue equation. I can just plug in the expression for A from here and left multiply by M inverse. Then you will see that B times the vector is lambda times the same vector. So lambda is an eigenvalue of B, but the vector itself is different. Corollary to that is that AB and BA have the same eigenvalues, which will come about because you can take M, the similarity matrix that you are using, to be B, and then you do the multiplication. Then you can prove that AB and BA are similar to each other, and so they have to have the same eigenvalues. Some examples. So I have this 2, 1, 1, 2. Eigenvalues should add up to 4 because there is a trace, and the product of eigenvalues should be 3. So that is because 2 times 2 minus 1 times 1, that is 3. That is the determinant. So you will see that eigenvalues are 3 and 1, and if you plug in, you will see that the eigenvectors are actually 1, 1 and 1 minus 1. So you can see it here. If I take 1 and 1, I'll add this guy with this. I get 3 and 3. So that is 3 times 1 and 1. So with eigenvalue 3, I have the eigenvector 1 and 1. If I take 1 and minus 1, that is 2 minus 1, 1 minus 2. That gives me 1 and minus 1. So that is an eigenvector with eigenvalue equal to 1. Okay? So if I take the matrix I'm using for similarity as the eigenvector matrix, I get the eigenvector matrix 1, 1 and 1 minus 1, and I get similarity right there. Some properties. Let me just go through the properties of similar matrices. Take some other invertible matrix M. So this is invertible, and the inverse. So swap diagonals 1 and 1. So swapping 1 and 1. Change the sign. So 0 and minus 4. And determinant here is 1 times 1 minus 0. So determinant is 1. So that is easy. So that is the inverse. So if I do inverse times matrix times the other matrix, I get some matrix that looks very different from A. You wouldn't know why these matrices are similar, but let's look at the trace and the determinant. The trace is 6 minus 2, that is 4. The determinant is minus 12 plus 15, that is 3. So same trace and same determinant, which it has to be because they have the same eigenvalues. So some properties, they have the same characteristic polynomial. You can write down the characteristic polynomial as lambda minus each eigenvalue multiplied. So it's the same, but you can prove it in a different way, fancier way. In the textbook you will see the proof. They have the same determinant because it's product of eigenvalues. And if A is positive definite, so is B because same eigenvalues. The trace is the same because sum of eigenvalues. Same rank, that comes from the Sylvester's law of inertia, because the number of positive pivots is the same as the number of positive eigenvalues, and you can just see that the number of pivots will be the same. The number of pivots is the rank. And one extra thing, almost purely mathematical here, is that similarity is what they call an equivalence relation, which means it's reflexive. A matrix is similar to itself. It's symmetric, which means if a matrix is similar to another one, A similar to B means that B is similar to A. And it is transitive. A similar to B and B similar to C would mean that A is similar to C. Proof is very easy to prove all these things. One thing I want to say is about the diagonalizability, the connection between similarity and diagonalizability. So we know that if A is similar to B and they have the same eigenvalues that we know, so we know that they will diagonalize to the same eigenvalue matrix if they are diagonalizable. So people use this as a definition of similarity. A matrix is similar to another matrix if they both diagonalize to the same eigenvalue matrix. This is fine as far as it goes. Oh, by the way, by same, we are allowed to shuffle the eigenvalues because there's no information in the order of the eigenvalues in the eigenvalue matrix. The shuffling is okay. So same diagonal matrix means same up to a change in the order. So it basically means that similar matrices form something like families of matrices with the same eigenvalue matrix. So all the matrices that diagonalize to the same eigenvalue matrix are similar to each other and they form a family. If it is a different eigenvalue matrix, then there's a different family. So infinite number of families. Our definition of similarity using diagonalizability is a bit incomplete, because if something is not diagonalizable, then how do you say similarity? What do you say about similarity? That's where the next topic, called the Jordan normal form, will come in. It's also called the Jordan canonical form, like I told you. Canonical is a word that mathematicians love. So Jordan normal form will take us to the next topic, called Jordan blocks. So let's look at diagonalizability. One thing that we know is that if the eigenvalues are distinct, the eigenvectors are linearly independent. And we know that if the eigenvector matrix S is invertible, then the matrix can be diagonalized. So if the eigenvalues are distinct, the matrix S is invertible because columns are linearly independent. But if the eigenvalues are repeated, you're not sure. It may or may not be diagonalizable. So repeated, another bad word for it is degenerate. But what we should know is that real data in data science, you seldom come across degeneracy, because the data points tend to be measurements and there's statistical fluctuations, etc. So there's no degeneracy typically. So if you take the identity matrix, all the eigenvalues are just 1, because eigenvalues are the values that are sitting on the diagonal. They are repeated n times, so that n times degenerate, but it is diagonalizable. In fact, identity matrix is diagonal to begin with. There's no extra effort needed to diagonalize it. But if you remember the shear matrix, that was not diagonalizable. The general form of shear matrix is lambda 0 a lambda. If I look at the eigenvalues here, they're going to be lambda, and it is twice repeated, so degenerate. The algebraic multiplicity is 2, but there's only one eigenvector. The algebraic multiplicity is 2, geometric multiplicity is only 1. Geometric multiplicity is smaller than the algebraic multiplicity, and that is the bad situation. In that case, your matrix is not diagonalizable. Algebraic multiplicity greater than geometric multiplicity means not diagonalizable. So let's talk about Jordan normal forms. So let me write a matrix. I'm going to call it J for Jordan, 1 for the size, and lambda for some value on which it depends. So this is a 1 by 1 matrix, lambda. I'm going to write J2 lambda, that is a 2 by 2 matrix, that is lambda in the diagonal, 0 here and 1 here. So if you look at it, you recognize the shear matrix. So this is not diagonalizable. And the third one is going to be lambda, 0 here, 1 here, 1 here, and 0 there. Okay, so I have this thing here that is called a super diagonal. That is one column to the left and one row above the diagonal, the main diagonal. That is called the super diagonal. So I have the repeated eigenvalue along the diagonal and once in the super diagonal, and that is the Jordan form. So you can write it for any one of them. Jk lambda will have this will be k by k matrix, and the diagonal element jii will be lambda. The super diagonal, that will be just 1. So if you have distinct eigenvalues, then they will form Jordan blocks of size 1. And if you have repeated with algebraic multiplicity is equal to geometric multiplicity, they will still form Jordan blocks of 1. But repeated with algebraic multiplicity greater than geometric multiplicity, then they will start forming Jordan blocks of 2 or 3. Okay, so that is the idea. So here I have, for J3, I have an algebraic multiplicity of 3, but the geometric multiplicity is still 1. So Jordan block is a square matrix. The repeated eigenvalue will be along the diagonal, once along the super diagonal, which is just one row and one column above the main diagonal. And each Jordan block will have an algebraic multiplicity same as its size and a geometric multiplicity of 1. So algebraic multiplicity is k, the size, and geometric multiplicity is 1. Now, based on this, there is a theorem that says every square matrix is similar to a Jordan matrix of the same size, and the Jordan matrix is called J. And the definition of Jordan matrix is a matrix that is made up of Jordan blocks along the diagonal. It's going to be zeros below the diagonal and eigenvalues along the diagonal and ones here and there in the super diagonal. And Jordan theorem says that every square matrix is similar to that. So it is possible that there are matrices that you cannot diagonalize, but Jordan form is the closest you can get to a diagonal form. Okay? So that is the genius of this